Hey Siri, open the curtain. If you'd like to build this project yourself, you'll find all the necessary files in the video description. You can download the circuit schematic, the source code, and the 3D printable parts shown in this video using the links below. Here are the components used in this project. First, I used a geared stepper motor. This model is easy to find, and thanks to its built-in gearbox, it provides enough torque to drive the curtain directly. For the microcontroller, I chose the ESP32-C3 Super Mini. It's an excellent choice for projects like this. Since it has built-in Wi-Fi and Bluetooth, it makes developing IoT devices much easier. To control the motor, I used a ULN2003 stepper motor driver board. This driver is commonly sold together with the motor, so it's also easy to find. For the power source, I reused the battery from an old mobile phone. In addition to these, I used two power management modules. The first one is a lithium battery charging module. The second is a step-up converter that boosts the battery voltage from 3.7 volts to 5 volts. When designing this project, I originally planned to include a solar panel together with an MPPT charging module. Unfortunately, the solar panel I purchased couldn't provide the required voltage, so it wasn't able to charge the battery. If it had worked properly, the entire system could have operated as a self-sustaining setup without requiring external charging. While developing the software, I tried to anticipate situations that could cause problems for the end user and design solutions for them in advance. For example, the curtain should still be usable even if your phone runs out of battery or your internet connection goes down. To make that possible, I added two physical buttons. Pressing either button briefly will make the curtain continue moving until it is fully opened or fully closed. If you want to stop the curtain at any position in between, simply hold the button until it reaches the desired position, then release it. The curtain will stop exactly where you want it. As you can see, this system doesn't use a sensor to directly detect the curtain's position. Instead, the ESP32 keeps track of the curtain's position by counting the steps taken by the stepper motor. Over time, systems that rely on this method can experience calibration drift. For example, if the curtain gets stuck or is unable to move for any reason, the ESP32 has no way of detecting it. It will simply continue counting motor steps as if the curtain were still moving, causing the stored position to become inaccurate over time. To solve this problem, I added a calibration mode. To enter calibration mode, simply press and hold both buttons simultaneously for 3 seconds. Once the calibration mode is activated, the onboard LED indicates that the system has entered this mode. While in calibration mode, the motor can rotate freely in either direction without any movement limits. This allows you to set the curtain's fully closed position. Let's assume this is the fully closed position. To save it, press and hold both buttons again for 3 seconds. The system will return to normal operating mode and store the new calibration value in memory. Now, if the curtain is already fully closed, sending a close command won't cause the motor to rotate again. Instead, when you send an open command, the motor rotates for the calculated travel distance and fully opens the curtain. Now let's move on to the code. First, let's take a look at the libraries used in this project. To integrate the project with Apple Home, I used the HomeSpan Library developed by Greg Berman. This library supports iOS devices. If you'd like to learn more about it, I'll leave a link to its GitHub repository in the video description. Right below the library declarations, you'll find the pin assignments used in the project. These 4 pins are connected to the stepper motor driver. Below that are the pins assigned to the buttons. The onboard LED is connected to pin 8. The next section defines the delay values used to control the speed of the stepper motor. This part is particularly important because there's a trade-off between speed and torque in stepper motors. As the motor spins faster, it produces less torque. After extensive testing, these values gave me the best overall performance. You can also experiment with the value 1200 to find the settings that work best for your own setup. The following section defines the curtain's travel distance. This value represents the total number of motor steps required to move the curtain from the fully open position to the fully closed position. It's one of the most important parameters you'll need to adjust based on the dimensions of your own curtain. If you want to calculate it more accurately, you can use the curtain length, the fabric thickness, and the diameter of the roller tube to determine the required number of motor steps. At the end of the code, you'll find some basic information that identifies the device. This includes the manufacturer name, model name, and serial number. You can customize these values however you'd like for your own project. Just above them, you'll also find the 8-digit setup code used for pairing the device with your phone. The HomeSpan library also supports QR code pairing. However, I won't be covering QR code generation in this video. I'll explain that in more detail in a future video. Even without a QR code, you can still pair the device manually. Simply enter the 8-digit setup code in the Add Accessories section on your phone. Next, let's configure the Wi-Fi settings. To do that, we'll need access to the serial monitor. I'll upload the firmware to a new board so we can go through the setup process. Before uploading the firmware, there's one important thing I'd like to mention. The ESP32-C3 Super Mini comes with 8 megabytes of flash memory. This memory can be divided using different partition schemes. Since this project requires quite a bit of flash space, you'll need to select the huge app partition scheme in the Arduino IDE. Otherwise, even if the code compiles successfully, it may not fit on the board. Now let's upload the firmware. While the firmware is compiling, let's take a quick look at the board's specifications. First, the board only supports 2.4 GHz Wi-Fi. Unfortunately, 5 GHz Wi-Fi isn't supported. That means both your phone and the ESP32 must be connected to the same 2.4 GHz Wi-Fi network during the initial setup. The specifications also confirm that the board includes 8 megabytes of flash memory. According to the manufacturer, it's suitable for applications such as smart home devices, industrial automation, and portable electronics. One feature that's especially interesting for battery-powered projects is its power consumption. According to the datasheet, the current consumption can drop to around 5 microamps while in deep sleep mode. That's a significant advantage for projects that need long battery life. At the moment, my software doesn't include any power-saving optimizations. However, adding support for these sleep modes is one of the first improvements I plan to make in future versions. Now let's take a look at the serial monitor. As you can see, it displays information such as the device's IP address. It also prints the message, "Smart Curtain is ready." If you send a question mark through the serial monitor, the ESP32 will display a list of available commands. To configure the Wi-Fi settings, it tells us to send the letter W. After sending W, the board scans for nearby Wi-Fi networks and displays them as a list. The SSID of my network appears here. After entering the corresponding number and pressing Enter, the board asks for the Wi-Fi password. Once I enter the password and press Enter again, the Wi-Fi credentials are stored in the board's internal memory. This means the settings are preserved even if the power is disconnected. The board will continue using the saved Wi-Fi credentials unless you modify the firmware or erase its memory. Finally, I'd like to share one more idea for improving this project. There are magnetic contact sensors that are commonly used as part of home security systems on doors and windows. By adding just one of these sensors, this project could function not only as a smart curtain controller, but also as a window status sensor. That way, your smart home system could also determine whether the window is open or closed. If you'd like to expand the project, this is one of the features you could add. That's all for this video. Thank you for watching. I'll see you in the next project. Take care. Like many engineering projects, this one started with a simple personal need. For example, the HomeSpan Library used in this project was originally created by Greg Berman because he wanted to integrate the range hood in his kitchen with Apple Home. My smart curtain project started in a very similar way. The window in my room faces east, and my bed is right next to it. If I forgot to close the curtain before going to bed, the morning sunlight would shine directly on my face, which made waking up pretty unpleasant. At one point, I started wondering, could I automate this curtain? Then that idea evolved into a few more questions. Could I control it from my phone? Could I operate it using voice commands? And that's exactly how this project began.